So welcome students. So in this question you're given two statements. So the first statement is A is a relation x comma y belongs to R such that y minus x is an integer. You're given that this is an equivalence relation. You're asked to check whether it is true or false. And the second statement is B is x comma y such that they belong to R cross R and x is equal to some alpha times y for some rational alpha. So you're asked to check the equivalence of these two statements, these two relations. So if you go for the first relation A is set containing x comma y such that y minus x belongs to integer, right? So if you want to check for reflexivity, so you have to check whether this relation will be true, will be always true for x comma x, right? So if you take x comma x, where x belongs to real number, so do you see that x minus x is always equal to 0, which belongs to z? So if you take the element and the same element, the difference between these two will be equal to 0, which is always a integer. Hence x comma x belongs to a for all x, right? Because for any x, x minus x will always be an integer. Hence it is reflexive. Hence the relation A is reflexive. If you go for symmetry, let x comma y belong to R or belong to A. Let x comma y belong to A. This implies x minus y belongs to z. This implies y minus x also belongs to z. Because if x minus y is an integer, y minus x is also an integer. And this implies y comma x belongs to A. Hence the function is symmetric. Hence the relation is symmetric. If you go for transitivity, x comma y and y comma z belongs to A implies x minus y and y minus z both belong to integers. So if x minus y and y minus z belongs to integers, the sum of these two should also belong to integers. This implies x minus y plus y minus z should also belong to integers. Y and y get cancelled. This implies x minus z belongs to integers. And this implies x comma z belongs to A. So if x comma y and y comma z belongs to A, x comma z should always belong to A. That means the relation is transitive. The relation is transitive, right? So the relation is reflexive, symmetric as well as transitive. Hence the relation A is equivalence. So next, if you go to the second relation B, so element x will be related to y if x is equal to some rational number times y. So if that is so, these two elements will be related. So let us check for reflexivity. So let us take x comma x. Let us take the element x comma x. So can I write x is equal to 1 times x? X is equal to 1 times x, right? That means every element can be written as 1 times the same element, irrespective of what this element is. So I can find some alpha such that x is equal to alpha times x. Hence x comma x belongs to R for all belongs to B, belongs to the relation B for all x belongs to R. Hence my relation B is reflexive. Let us check for symmetry. So let x comma y belong to B. Let x comma y belong to B. That means x will be some alpha times y. Some alpha times y. This implies y is equal to 1 by alpha times x. So if alpha is a rational number, can I be sure that 1 by alpha is also a rational number? If alpha is a rational number, can I be sure that 1 by alpha is also a rational number? Mostly true, but there is one exception. There is one exception. That is when alpha is equal to 0. When alpha is equal to 0, 1 by alpha will not be a rational number. Hence, there is one case where there will be a problem for symmetry. That is, if you have something like, so if you have the element 0, 5. If you have the element 0, 5, this will belong to B because 0 can be written as 0 times 5. So there is some rational number such that x is equal to some rational number times alpha times 5. But if you take 5, 0, so can you write 5 is equal to some rational number times 0? 5 is equal to some rational number times 0. Can you write this? No. That means 0 comma 5 belongs to B, but 5 comma 0 does not belong to B. This does not belong to B. This belongs to B. So there is an element of the form x comma y which belongs to B's, but y comma x does not belong to B. Hence, have a counter example. So symmetry is not valid. You don't need to go for transitivity again. So symmetry is not valid, hence this is not an equivalence relation. So statement 1 is true, statement 2 is false. That's the answer to this question. Thank you.